last time we made the point that now that we know the architecture of this free-phase solution, that's free-phase solubility area, which sits in the subsurface, to calculate that source region and where that might get transported to in dissolved form. What we'd like to do is to be able to calculate things like what concentrations it might arrive in and when it might arrive. And so, just by way of recap today, maybe we'll talk a little bit about that, just to pull out the important components. And then we'll go to talk about some methods of being able to define solutions that are slightly more accurate for both one-dimensional flows, as we've kind of talked about in schematic form last time, and also for three-dimensional flows to represent real aquifers. So that's our plan today. So to recap, you'll remember that we were talking about the advection-dispersion equation. And we made the point that we don't necessarily need to understand the derivation of that, but it is useful maybe to be able to understand exactly what the characteristics of that are. And so you'll remember that it looked something like this: an accumulation term, a dispersive term, with appropriate coefficients attached to it, which we'll explain in due course, and an advective term. And the geometry of this is something that, if we look in plan view, in terms of x and y, and we look at, for instance, a plume emanating from some location, then we said that we thought that plume would start, you could imagine this plume would start looking like this, where this might be 1 ppm, this might be 10 ppm, and I suppose also parallel to this, we thought about this in terms of, if I can draw this. Don't you think my drawing skills are getting better? And just have this idea here. This is this upstream thing, and this is for transport along here, which is the advective velocity in the x direction, which is the same as the advective velocity in the x direction. And this is the geometry that we're dealing with. And so this evolution of this plume, whether it's in one dimensions with this kind of plug flow geometry that, this plug flow geometry that we have here, which would look something like this, C over C0 on this axis, from 0 to 1, and this also would be the x direction. These are all common to each other. They're the same geometry. What's different between this system and this is that this is a one-dimensional system, in which case this y term would drop out, and this is a two-dimensional system, or maybe a three-dimensional system, because it also has the z direction coming up, that it would have an extra term here actually, but let's not worry about that now. We know that these terms are dispersion. So in other words, we know this is And it is just a mass balance. It says that whatever comes into this control volume by diffusion or dispersion, plus however much comes into it carried by advection, physically carried by the bulk motion of the water. This is the water velocity. What doesn't leave has to accumulate. The balance between what comes in and doesn't go out by either of these two mechanisms, transport mechanisms, has to accumulate. And so if we were to draw exactly what this would look like, then this would be the part, let me do it in black, just because I can. This would be the part. Oops. This is the part that looks like this, where this distance here we can get from advective velocity is equal to length over time. If this is length, then this would be advective velocity times time, by definition. And the dispersive part is this same part, if you like, but is the portions that result in spreading. So this is where this diffusion coefficient, PL, is not equal to 0. And this would be the case for where this dispersion coefficient is equal to 0. This is just the same thing. So that's kind of our understanding. So understand what these physical terms are. It's useful that we have a differential equation to do it, because we can use that to solve things to give us actual numbers on these. And I guess we did say last time that we're taking this value here, if this is relative concentration, that varies between 1 to a half to 0. We've always made the point that this intersection is exactly at the point of this advective length, distance traveled, and that it goes through this 50% mark. And so we'll examine whether that's the case. And you can imagine that it's not the case, because this would imply that, for instance, if the velocity is 0, this propagation of this plume has to be 0. And we know that if you leave liquid in a beaker, a solute in a beaker, it'll spread. And so this can't actually be the case. What else do we know? We know that this is advective velocity in the x direction, which is equal to permeability over viscosity, change in head with length, multiplied by 1 over porosity. This term here is the Darcy velocity in the x direction. So this defines the rate at which this propagates downstream. There's only one component here, because there only is one component of advective velocity. You could add another term on here, I suppose, if I clear this. Oh no, it doesn't quite do that. I could add another term here, which would be Vy, advective d, I can't write it, dc dy. But because this term here is 0, that doesn't exist. So you see some symmetry between these two terms, each of these two terms. That's the reason that doesn't exist, is because the velocity in the y direction has to be 0, because this is the principal direction that's carrying the flow. I guess the other thing we know is that for these terms here, we talked about longitudinal dispersion coefficient. It's equal to a longitudinal dispersion coefficient multiplied by an advective velocity in the x direction, plus a portion which is equal to molecular diffusion. We know that this molecular diffusion magnitude d star is equal to the true molecular diffusion in a solute, in a beaker, multiplied by something that accounts for the tortuosity of the flow path. And we talked about that last time. We know that the units of this are well, we could get them, I guess. What are the units of this? We know that this is mass over volume, milligrams per liter or kilograms per meter cubed, whichever we prefer. It's throughout this equation in every term, so we don't have to worry about it. But we know that each of these terms without this concentration have to be in units of 1 over seconds, right? Just 1 over time. So the units of this have to be 1 over seconds. So that means that the units of d longitudinal dispersion coefficient multiplied by 1 over x squared, we've taken this out, have to also be equal to 1 over seconds. So that implies that the units of this have to be in units of length squared over seconds, just by rearranging this equation. And indeed, that's exactly what it is. It's in meters squared per second. And so this is in meters squared per second. It's getting a bit crowded here all of a sudden. So if this is in meters squared per second, this is exactly the right units for this, for diffusion coefficient, molecular diffusion coefficient. This is just a multiplier that has no units. This is in units of meters per second, velocity, and so by definition, this has to be in meters. And as we'll find out later on, that if we look at a plume, and that plume happens to be a length of L, then this longitudinal dispersion coefficient is typically equal to the length of the plume divided by 10, which is a strange result because you'd think it would be a property of the medium that it's flowing through. But it turns out to be more a property of the geometry of the plume. This is the length of the plume, whatever size it currently is, and divide that by 10, and you have this unit. This is units of length, this is units of length. So that's kind of our, what we talked about last time, what we finished up with. So that's kind of where we are. So we have a partial differential equation. We kind of understand, hopefully, exactly what it physically means in terms of this term represents this plug flow term. This term represents this longitudinal dispersion in this axis. This term here represents the spreading that occurs in this direction, how wide it gets. The bigger that term, the wider it gets as it goes downstream, down gradient. And this is the term that allows this all to happen. And so if you want to think about, well, perhaps you don't want to think about this equation at all, but if you want to think of this equation, really what it's doing is it's taking a little cell that is dx by dy in size, and it's saying whatever comes into this cell from upstream by dispersion, whatever gets transported down by advection, and the balance between what goes in the upstream side and what comes out the other side is what the accumulation is. And so if we apply appropriate boundary conditions to a geometry like this that represents maybe this, you could think about this core, this longitudinal part of the reservoir, one-dimensional reservoir, as being a representative of this, or we could think of it as a three-dimensional geometry as well. So that's kind of where we are, right? So I made the point that this is very convenient for us to think of, that this breakthrough point here would be 50% concentration, and it would occur at whatever time is given by this plug flow behavior. But for the rationale that if there is no plug flow, in other words, the advective velocity was 0, and it was spreading only by molecular diffusion, then that would suggest always that this would be at the 0 axis, and there would be no spreading. And so the question is, how do we figure out exactly what this plume looks like as it goes down gradient? And so what we'll attempt to do is we'll try and define that for these two different kinds of geometries. For one-dimensional flows, which would be looking like this, and for three-dimensional flows, which would be looking like this. You think it's 2 dimensions, but really it's 3 because it's got a vertical direction that comes out of the page because we're looking at it in plan view. Okay, so, right? So that's what we'd like to do. So we've kind of done this. We've got these equations. We've simplified it. This is really what we've talked about. You see this kind of geometry here that we're talking about. We've already done that. We'd like to be able to look at some solutions to this. And so what we could do is, if we're trying to define this behavior, we could think of this in a very simple way as the reservoir, or aquifer, I guess, for this thing, this consideration, has this advective velocity. It has a concentration here that is turned on at some time like this. This is C over C0. This is time. This is the condition at this upstream face. And this is the behavior here, which is this. If you look along the length of the core, then the response is something like this. This is a length which is equal to an advective velocity times time. And if we look at the response at the downstream side, then this response, if I can fit it in, haven't left much space. This would be time. This would be relative concentration, C over C0. And it would look like this. So these are the basic features that we'd like to be able to prescribe. And we know that if dispersion is occurring, then these curves will look like this. They'll be spreading ahead of this front, kind of fingering that we explained last time. And in terms of the arrival at some compliance location, there'll be an early arrival part, and there'll be a long tail to it to mean that the last part at 100% concentration takes a longer time to break through. So that's the physical system that we'd like to look at. We can use what I referred to analytical methods, which is what we'll do here, and that's basically solving that PDE using some techniques, which we won't worry about. We'll just look at the solutions. Or we could solve it numerically. And those two different kinds of solutions fall in two different utilities, I suppose. Analytical solutions will give us a very fast calculation to be able to understand exactly what's going on here. Numerical solutions would be more involved, but would be able to include things like heterogeneity and mixtures of beds and different permeabilities within our system, which might be important or they might not be. So in either case, we can look at those. So that's exactly where we're attempting to go. And so I guess this is, let's come back to that. So these are the solutions. So we're going to look at behavior, again, only to look at what the solutions of these are. And so the geometry that we would take would be this core. The upstream location is where we apply the boundary condition on this upstream face, which we turn on at some time. And we look at the transport of this downstream. And so we can get two responses. One would give us this response of the concentration within the sample, which would be this. And the other one, where this is length and this is relative concentration. And the other one that we would be interested in would give us a change in concentration with time, which again is this relative concentration, which we always use between 0 and 1, just because it's convenient. So those are the two things that we're interested in. This is what we called B before, and this is, we didn't call this anything. And so you could imagine there are a number of different boundary conditions we could apply. The one we've applied has always been that we turn on the concentration upstream, and I guess we've drawn that, and I'll draw it again, just for, which is this. The concentration gets turned on at time 0. This is time. So the one that we've looked at before is this one here, so-called first type boundary condition. These are the terms that are used in FETR, by the way. How many people have FETR, just out of curiosity? 1? Is that right? Fine. Okay. Second type would be where you put it in at a constant rate. So in other words, the rate at which you pump it in is constant. And the third type would be a flux that's changing over time. So we'll really only talk about the first one. It's the most useful to us. And so we'll end up with some expressions that look a bit like this, like we've expected from this. So this is it. The solution is by stretching or asking? Stretching. Okay. Yeah. It's by Ogata and Banks from the early 1960s. When I was alive, but you weren't, by the way. As you know, of course. I was barely alive. Well, you might say that's the case now as well. Anyway, very chirpy today. I am. So anyway, so this is geometry. So this is the upstream boundary condition that we talked about. We called it this kind of A upstream boundary condition. And all of a sudden at time t0, we turn it on to be some number 1, which is the initial concentration. Could be any concentration, of course. That's our normalizing magnitude. And I suppose the only interesting result is that we choose in this core a location, and that location is some location downstream. So the x value that we choose is what's happening at this location L. L could be 10 meters, could be 1,000 meters, could be whatever we choose it to be. And we could use that to say something about how the concentration changes as a function of time. And as I say, we'd like to say something about these two different things. What does this distribution of the concentration look like in the aquifer? And at a compliance point, what is the RTD, residence time distribution? Always good to use acronyms in interviews to show that you know something. Oops, not that one though. And the solution for that PDE with those boundary conditions is this, here. It says that the concentration changes with the value of the upstream concentration and a number of different factors. We could, of course, divide both sides through by C0, as is done here. And actually, yeah, let's do this, because you think you'd never use these things. Buckingham Pi. Remember Buckingham Pi? How many, what's the minimum set of parameters, non-dimensional parameters that will define this behavior? So we know that C over C0 is some function of a number of different parameters. What are the parameters? It's how far we are downstream. It's what the advective velocity is. It's a function of the dispersion, longitudinal dispersion, and it's a function of time. Don't you just love this? No one's having nasty flashbacks, are they? Not if you're looking at your phone. So, what do we do for Buckingham Pi? Units. What's the units of this? Okay, some have. So we have 4 parameters. We have length and time represented, but no mass. Mass is involved in here, but actually it's the ratio of each other, so we're not worried about that. So we have length and time represented, so 2 components. And the number of pi groups are going to be equal to 4 minus 2. So we have 2 pi groups. 2-dimensionless groups would define this behavior. It turns out that these 2-dimensionless groups, which I've almost overprinted here, are these here. This is called Peclet number. French, Peclet number. And it is the ratio, like Reynolds number is the ratio of inertial to viscous forces. This is the ratio of advective flux with an L to dispersive flux. Can you see that, by the way? Yeah, you can see. And so you can see this. This is the advective flux, and this is dispersion on the bottom. And so that's an important number. And so when this is 0, it means the process by transport is only by diffusion. When it's a very big number, it means that diffusion is irrelevant because it's been carried so fast by the groundwater flow that it goes a long way before it can spread out. And the other one is called, well, we'll call it pore volumes. Which is, in this parlance, in Fedor's parlance, T sub r, which is the advective velocity. So these are both advective velocities, even though it doesn't say this, times time over the length. And so this also actually called a Courant number after the, also French, Courant number. Le numéro de Courant, n'est-ce pas? And so this is, no. In pore volumes, it means that this term on the top, right, the length that you traveled downstream, I think we said that this length that you travel downstream is equal to advective velocity times time. And so it's the length traveled downstream divided by the length downstream. And so it means that if you have a plume that's being carried only by plug flow, by the time it gets to the end of the core at length L, that's one pore volume. It's invaded one pore volume of the whole core. So that's physically the meaning of it. If you look at Courant number is something that's used in numerical modeling to define stability. And basically it says that if you have a little cell in which you divide your model up into a whole bunch of elements or cells, if in one time step the solute has come in one side of the element and exited the other side, then your time step is too big because it doesn't have any memory of the thing going through, the front going through that. And so it's a measure of stability for numerical models. It doesn't matter here. And so when this is equal to 1, 1 equals, is the front is at the downstream location. In other words, it's at location L. So, but you know that. All right, and so we could do, maybe we don't need to, we could derive that. Do you want to do it? I don't know whether we want to do it. No. So what you could do is that we know that we want to get this expression to these terms, Vx over dl. So this for sure is the Peclet number already, right? And so what I suppose we'd want to do is we'd want to be able to take this term here. If you divide this term through by L, for instance, so if you multiply both top and bottom by L, you get this, which is Vt over L. This is the Courant number. And you'd also have a term that would be this over L as well. I'm not going to go through it. I don't think we need to. You could rearrange this. You're seniors now. You could rearrange this in terms of these two parameters. And these parameters will exactly define this behavior. So you remember the strength of Buckingham pi and non-dimensional analysis is that now this says that the relative concentration is described uniquely by these two parameters, nothing else, but by these two parameter groups. And so what we could do is we could use this equation, which clearly is a function only of these two parameters, Peclet number and pore volumes, and we could plot it out in some way. And so one way that we could plot it would be to look like this, which you also see within these notes if you go back a couple of pages, which is here. And this figure is merely showing It's good color. It's showing two axes. One on the bottom is pore volumes, which is, what did we say? Advective velocity times time over length of downstream. We said that when this equals 1, it means that the plug flow front has gone all the way through the core to the end of it, which is this point here. And so what we could do is we could look at drawing this curve here, and this would be our residence time distribution. So these curves that are here would be for what we call plug flow, what I call plug flow. In other words, it's arriving as a plug. All of a sudden the concentration goes from 0 immediately before it arrives to 1 as it arrives, and stays that all the time. So this would be for a Peclet number equal to infinity. And you see that this is just a graph of relative concentration, C over C0 between 1 and 0. We said it is a behavior as a function of two parameters, the pore volumes and Peclet numbers. And so if we, just to back out of this, if we look at this expression that we have, by definition we have three properties. Relative concentration is a function of Peclet number and pore volumes. We can plug some numbers into here and get this. And the graph we get is exactly this. So we'd use that equation. We'd choose, say, a Peclet number of a single value, say we use it as 100, which is on there. And if we calculated that equation for Peclet number of 100 for different values, substituting different values of this pore volumes, then we'd end up getting this curve, which is this curve here. And so this curve represents a Peclet number of 100. This curve, which is not so obvious, represents a Peclet number of 10. And this curve, this little piggy, represents a Peclet number equal to 1. And you remember that Peclet number we defined as the ratio of advective to dispersive fluxes, so velocity times length over dispersion coefficient. To dispersive. So the outcome of this, and these dashed regions are for the different boundary conditions. So this is for the particular type A. So this is our type A boundary, type 1 boundary condition. The one that we've just looked at the solution for. And so the green curves are for that. The other dashed curves are for slightly different boundary conditions, which we won't worry about. But, so the bottom line is that we've always said that this breakthrough curve occurs when we're at 0.5 relative concentration, which would be this point exactly here, if it's not too muddled. That's certainly the case for Peclet number of infinity. It's kind of the case for Peclet number of 100. It's not so much the case for a Peclet number of 10, which is here. And it really isn't the case for a Peclet number of 1, which is here. So this is for 1, and this is 10. And so we have to be a bit careful with this. So these things that we've used so far quite freely, and it's been okay, that have given us these rough breakthrough times and concentrations at breakthrough going from 0 to 100 aren't necessarily always true. They are true maybe if the Peclet number is greater than 10, I guess, or or 100 if you wish. But they're not true otherwise. They're not true because they give us, at this breakthrough time, concentrations which are higher than we'd expect, right? They're larger than the 50%. And that is because there's been spreading dispersion ahead of the front, which then arrives earlier. And if we're looking at the first breakthrough times at 50%, then the numbers that we would choose would be this, which is PE equals 10, and would be this number here, right? If Peclet number was equal to, sorry, that's wrong, right? This is 10. This is 1. So these locations here, in terms of the breakthrough time, and these locations here in terms of the breakthrough concentration at the, the expected 1 pore volume time, are wrong if we use the expressions that you've been using. So you need to be aware of that. And so this is kind of a messy figure. I realize that. But the cameo of this is this one figure at the bottom of this one page here, which is, I hope, perhaps less messy. So this is exactly the same figure, making the same point. And that is that the breakthrough curves look a bit different. For Peclet number infinity, it's this vertical one. Peclet number of 100 is pretty close, it goes through here. But for Peclet number of 1, it's not true, nor 10. And that is because this intercept here is not 50% at 1 pore volume, and this arrival time, first arrival time, occurs before 1 pore volume has come through. And so if you wanted to physically think about what this looks like if you had a core, maybe that's useful to do. This is what the core looks like. Is if it was plug flow, and I'm going to erase this after I've done it, then this is physically what it looks like. This is the front that's going through here. It's solute laden at 100% on the left side. It's solute laden at 0% on the other side. And that's boring. But what it would look like if it's Peclet number of 1, and if I dash this across here, it's what we kind of drew maybe last time. Maybe this is what it looks like. These aren't fingers of DNAPL. These are fingers of solute being carried downstream. And so it's, if we have some portions of the reservoir, aquifer, not reservoir, that are high permeability and therefore flow occurs faster in them, then you'd expect that it would carry the solute down more quickly, and it would get ahead of the average hydrodynamic front that's moving through the system. And if some of it's getting ahead of itself, then by definition some of it has to lag. Some of it has to be slower than the average magnitude. And so you could imagine this fingering occurring where if you look at maybe halfway through that and you averaged across that surface, so 100% saturation, 100% concentration, 0%, 100%, 0%, etc. as you go down across here, then on average maybe you get 50%. So that's kind of the idea of what's happening. But I guess what this is saying is that really it isn't 50%. By the time this average front gets here, it would be 70% solute and 30% would be empty in that ratio. But that's physically what's going on. So be able to do that. I did pull, what do we else want to do? Yeah, let's do it. Let's do it. So anyway, so it's pretty straightforward, I think. I always say that, right? Everything's straightforward. I did put something on my desktop. So just for a bit of light relief, we could do the calculations for that. You probably can't see any of this, and I don't know how to make it larger actually. But this is just a plot of exactly, no, I don't want that. You'll see exactly what these are. So if we use, for instance, a Peclet number of 100, and we do this plot, then this is the breakthrough curve. So I can't draw on this. This is relative time, pore volumes. This is 1 here. This is 100% concentration, 0% concentration. So I can't very well draw a line here, but if you look at the cursor, for Peclet number of 100, the breakthrough time at 1 pore volume is 50%. If we change that number to something less, you'll end up with exactly the curves that we had before. So now at Peclet number of 10, this is 1 pore volume, and I'd say it breaks through at about 0.6. If you change it to 1, just like this is MATLAB, a free MATLAB. If you change it through to 1, so Peclet number of 1, then 1 pore volume occurs at, it breaks through at 0.7. This maximum magnitude now is 0.9. And so if you look at the numbers for this for the alternative curve, the other curve that we have, this is the curve looking at the concentration occurring from the upstream portion of the core going downstream. So this now is the length dimension. This is the end of the core. And so it means that upstream the concentration is held equal to 1. As you go downstream, this doesn't look anything like this step curve anymore, because now at the downstream location, the concentration at this particular snapshot in time, which is a time of 1, it's equal to this, and this is its diffusive profile. If you changed it to being an advective velocity or a Peclet number of 100, then you can imagine that it would look slightly different. This means that it's 100, it means it come through here, it's already broken through, it's gone all the way much further downstream, and so within our core, it's all equal to 1. And so it's easy just to calculate it. So the bottom line, I think, is that these expressions here, or this expression here, this one expression here, allows us basically to do those calculations. And you do have to know what the error function, complementary error function is on your calculator, but that's not particularly difficult. It's a function on in MATLAB or elsewhere. All right. So that's kind of our picture. So I think the take-home message for me, from what we've talked about today, is this figure here. And that is that we can't really rely on this simplified model in all cases. Maybe we have to have a Peclet number equal to something like 100, maybe 10. Certainly 100 is probably good enough for us before we can use the simplifications that you've used so far in this class. If the Peclet number is smaller than that, then you might think about doing something else which incorporates this. And in an intuitive sense, you know, it makes sense. What this is saying is if the Peclet number is equal to 0, what would this curve look like? Don't know what I'm drawing with my trackpad. I guess it would look like this. And that is because it really basically breaks through at 0 length at 0 time. Yeah. So in other words, you can imagine that if this is 100, this is infinity rather, this is 100, this is 1, you can imagine the progression of that it would get closer and closer to this axis. And this is saying that, well, I guess what it's saying is that if this pore volume thing is an advective velocity multiplied by a time divided by a length, if the advective velocity is 0, which is the case for a Peclet number of 0, then this is a useless parameter to use, basically is what it's saying. Because this is always going to be 0, and this parameter means nothing. And so I think as Peclet number gets progressively smaller, it'll just move closer and closer and closer to that axis. It'll never touch it. So good to maybe get a feel for this. Impressed? Yeah, good luck. Yeah, that's a nod, right? Yeah.
So it was a grin.
No, not you. It's the guy, your buddy in the hat. So, all right. So we said we talk about one-dimensional problems. So you could imagine that you could make your aquifer into this stream tube or this core, which is defining this behavior. Or you could also look at more sophisticated geometries, which would represent the case that we looked at when we introduced what we're doing today. And so this is what we've done. Bless you. And we might want to look at something that is still homogeneous and still quite simple, but would represent this physical geometry, which is a bit like this, right? You could imagine if you drew this perspective concentration through this plume here, it would look a bit like this. It would have some spreading around the front as you go across this high concentration to lower concentration, etc. And it would look similar. So we're going to talk about 3D flows. Okay, so we use the same expressions that we had before. Snowing or blowing off the roof. So, okay. So, you can imagine that we are, well actually, let me just back up. You could imagine that the other thing that we could do, you know that we talked about two different geometries. One is where you turn the concentration on upstream and you leave it there for all time, and it gives you this step function behavior downstream, the one we just talked about. The third of the Fetter solutions, if you look in Fetter's book, which you might not do if you don't have it, is for this spike concentration. So in other words, you have a small volume of free product in your aquifer. It dissolves out over some relatively small period of time relative to the transport period. And so the source concentration looks like this. It gets turned on at time 0, stays on for a while, and gets turned off when it's all removed. And so if you apply that particular boundary condition to the upstream of this, then you get a different solution. And so the downstream residence time, you know exactly what it looks like, right? This is time versus C over C0. Will look like this. Maybe it'll be spread out due to dispersion, right? This would be the dispersed example. This we think might be equal to time being equal to, well, what is it? Velocity is equal to length over time, so time is equal to length over velocity. Advective velocity as always. We think that this might be true because it has the same constraints as before that maybe it is or maybe it isn't. And if we looked at behavior along the length of this core and drew it in perspective, then the concentration will look like this if dispersion is equal to 0. And this if dispersion is not equal to 0. I guess it's greater than 0. You could draw if you wanted. And so these geometries might also be useful to us as well, because you might have a source which over the lifetime of that you're looking at it disappears because it gets removed, just like assignment 4, which is due today, right? Because it is Thursday rather than Tuesday. And the solution for that is similar. It's a function, relative concentration is a function of two properties, just as before. As you can see, this is this term here. Peclet number, pore volumes. This only contains Peclet number and pore volumes as well. But it includes a slightly different one, which is equal to the time of peak concentration. And the time of peak concentration is just this number here, which is 1 over Peclet number square root, I guess. 1 over Peclet number squared, square root minus 1 over Peclet. So it seems like a complicated equation, but I guess some reasonable values for this. If you choose, for instance, a Peclet number of 10 would be easy, right? That gives you a max, the time at which the max concentration arrives at L. TR max arrives at x equals L. I think must be what it is. So what that would be, this would be 1, so 1 over 10 squared is a hundredth, so this would be 1.01 square root, which is about 1, minus Peclet number, which is 1 over 10, which is a tenth, so this would be about 0.9. If it was, let's do 100, 100 would be even better, right? So this is 1 over 100. 1 over 100 squared would be 1 over 10 to the 4, which is basically 1 again. Square root of 1 is 1, minus 1 over 100, which is 0.99. So this is saying that if the Peclet number is big, then this arrival time here really is equal to this advective velocity time. Right? It's really saying this. It's equal to when one pore volume occurs. It arrives downstream as soon as one pore volume has been traversed through the system. If the Peclet number is 10, then it arrives, the maximum concentration actually arrives earlier than it would have done otherwise, right? So this peak concentration arrives at 0.9 of the time that you'd calculate from this expression here. And as you go to progressively smaller Peclet numbers, I don't know, will 1 work? So this is 1 over 1 squared. This is 2. Square root 2 is 1.4-ish, minus 1, which is 0.4. These are all approximates, right? So it'll arrive really early. And so, in other words, it gets pushed downstream faster than you'd imagine otherwise. Okay? And so we can calculate that. If we know what that time is, then we can also calculate the relative concentration, in this case given as a function of the maximum concentration, which would be this, right? There is no constant concentration, but this would be the max. This value. The top of the peak, whatever the concentration is that you start with. And so that allows us to be able to calculate that. And so that's just another, maybe it's mathematical gymnastics, but useful. So 2 equations that are perhaps useful to you. Constant concentration upstream and a delta concentration, a Dirac delta concentration that's turned off. So far these have both been in terms of one-dimensional flows down this core. If we wanted to, we could figure out exactly what those would look like in a real aquifer, which you're looking at in plan view, which has a length down gradient, a width across the plume, and also a height of the plume relative to the vertical ordinate in the z direction, if you like. And it turns out that the solution for that involves something that we talked about last time, and that was, I'm going to do this just for the hell of it. You might remember that we made this point that if we start with our beaker of water and we put in this beaker of water our blob of ink and we draw a section across this, whoops, that's good enough, not vertical, to look at concentration. Then if we look at that concentration initially, then it looks something like this. And then at subsequent times it looks like this, progressively. And then progressively flatter and flatter. So this is T0, this is T1, this is T2, this is a radius, and this is a relative concentration. And so we made the point that this curve here, if we take it out, is basically a normal probability distribution. Very tall, and it never looks like this square. Well, I guess it does initially look like this square distribution, but at a point. at a single point, along this axis, and it spreads out. And so you kind of know what the properties of this are. That something like one standard deviation, for instance, if you were to draw one standard deviation, 1 sigma, the so-called 1 sigma, and either side of the mean, I think that means that 66.7% of this area, total area, is included inside that. I think it's that. The whole area under this curve. If you look at 3 standard deviations, 3 sigma, then I think that means that this contains something like, I think it's 99 point something. So the area between these lines. That's physically what it means. So 1 standard deviation means you're better than 66% of the folks and worse than 33.3%. So it's physically within here. So that's physically what it means. This you could think of as being the concentration, as we've drawn it here. And it turns out that, so one way that we could think about it, if this represents dispersion, and diffusion, which is this term, which is, let's do it, I'm going to write it, dispersion in the x direction, which is equal to longitudinal dispersion times advective velocity plus d star, diffusion, right? Remember? Mechanical mixing, tortuosity, and molecular diffusion, add them together. One is big when velocities, mechanical mixing is big when velocities are high, diffusion is big when velocities are small, or is the dominant process when velocities are small. And so this is this process of what's going on in the beaker. The other part of the beaker, not to don't insult your intelligence here, but the other part of the beaker is physically taking this beaker from here and translating it here. And so by the time you get here, then all of a sudden this ink blot looks like this. And on the figure that we had that explains that, that is physically, I have this diagram. I really like this diagram. I thought it was quite clever. Then I would, of course, right? Is this idea that you get these things going here, and you get these things going down here. So by the time you draw this diagram here, it looks different from the diagram here, right? So this is the essence of what we're doing. So advection is physically moving this beaker downstream, and dispersion is what's happening in the beaker as it goes downstream. Some of this mixing is due to mechanical mixing, dispersion, and because it looks exactly the same as diffusion, we lump these two terms together, mechanical and chemical mixing. So that's the whole essence of what we're doing. So we could use that exact same idea to be able to solve this differential equation. And in pictorial form, if you like, it looks something like this. And you know these terms: dispersion, advection, and accumulation. And so what you could do is, why don't we solve, if we know how to solve this diffusion process really easily, we know it kind of looks like a Gaussian distribution. if maybe what we could do is we could just solve the diffusion part of the equation, which is this. Solve this. We already talked about a solution for that very early on last time. Solve for this spreading of this diffusive front, and then just move it downstream by the amount that is suggested by this term here. So in other words, we physically carry it downstream by some length. Well, we carry it downstream at a velocity which is equal to the advective velocity. And that's what we'll do. And so that idea is embodied in this solution here. This is what this solution is. It says that the concentration at any point, x, y, z, and at any time, if you have a source that exists at this particular point here, what we can do is we can solve for the diffusive spreading of this thing, which will make a plume from this point introduced source, instantaneous source. So I guess this source, I guess we should say, is the same as equal to this spike of relative concentration. So it's this spike. And as it goes down gradient, it will get larger and larger and larger as it goes off the page, a bit like this. So it starts here. It gets carried downstream. By the time it's downstream, it's got bigger. Keeps on getting carried downstream, gets bigger and bigger. We can solve for this spreading because we know what that is. We know it looks like this bell curve, Gaussian distribution curve. And so long as we know as where this point would be at any given time, it would just be the velocity times time, then we can say exactly what this plume looks like in terms of what the concentrations would be at any point within here. Say here, which would be right here, right? So that's it. So this solution is basically this. It says that if you put a massive solute into your aquifer, if you know your dispersion coefficients, which are something like dx would be advective velocity times alpha x plus d star. So these terms, mechanical mixing, diffusive mixing, chemical mixing, in each of the x, y, and z directions relative to the plume that's evolving. So these are just material properties. This is a massive solute. This is an advective velocity. This is how long it's been since it started. And this is a location relative to the initial location of the plume. So the initial location of the plume is x0, y0, z0 in some way. It gets carried downstream in the x direction. So the advective velocity is in the x direction, which means that the advective velocities in the y direction and the z direction by definition are 0, because it's a principal direction. And this gives us the solution for that behavior. If you want to think of it a different way, then you could realize that really what this expression is, if you keep your coordinate system uppercase x, y, and z in the middle of exactly where the center of mass of that plume would be, as it's getting carried downstream at this velocity, so that any given time the length downstream is going to be the velocity times time, its product. This would be the center of mass. And then relative to the center of mass, this would be the equation. This is, so this coordinate system, big X, big Y, and big Z, uppercase, is centered on the center of mass. And so if you go out any distance from that, this would be uppercase X, uppercase Y, uppercase Z in this term here. Then you can figure out exactly what the concentration is within this plume. So it's just an exposition of this. If you look at the center of the plume, then by definition the coordinates for x, y, and z are 0. That means this term here is equal to 0, so it becomes 1. So e to the 0, I think, is equal to 1. And which means that the maximum concentration that you have is just going to be this value here. That's exactly what this is. And so that's maybe a more intuitive way of looking at exactly what's going on. Have a beaker, it's diffusing. We solve the diffusion equation to be able to figure out how widely it's spread and what the concentration distribution is in there. That concentration is a bell curve, which would look like this. With location. And so at any point within this plume, we can figure out exactly what this concentration is. The maximum concentration is going to be exactly bang in the middle of this at x equals 0. Putting x and y and z to 0 gives you this, and you can calculate what that mass would be. So it's an intuitive way of thinking about it. Parting shot. The last thing to think about is that because this is a bell curve, Gaussian distribution, and because we spent some time saying about 3 standard deviations, this means that 99% of the concentration or the mass is included within 3 standard deviations of this center of the plume. So the utility of that would be that if we wanted, for instance, if you have a plume, and if you could go to that plume and sample it so you knew how big the plume was, so that you immediately know how long 3 standard deviations is to the extent of this plume. I guess 3 standard deviations would be the length of the plume divided by 2, because it has 2 sides to it. If you could get that from being in the field, then the other simple relationship that exists is that 3 standard deviations is equal to this term here. And so if you can measure this distance, which you could do, right, if you saw the plume, then you have enough information to use this. You know this, it's a length. This is 3 times, not cube root. This is the time since the plume was started. If you know that, then you have everything you need to be able to calculate the dispersion coefficient, which you'd like to know. And so you could, in the field, figure out, if you knew exactly what your plume looked like, you have enough to be able to calculate the dispersion coefficient just by rearranging this, right? 3 standard deviations divided by 3 square root multiplied by a half and divided by time is equal to dx. And dx is equal to alpha x, or alpha L, advective velocity plus molecular diffusion. Typically we know this. If you know how far downrange you are, if you know this and you know how long it was, then typically you know velocity. If you know velocity, then if you're able to measure this in the field, then you can calculate exactly what this is. And so that's kind of one possible calculation sequence if you had a plume. So I think that's all I'm prattling on about today. Everything clear? Crystal? Yeah, Jonathan.
Wouldn't that part with the 3 standard deviations and let 3 be squared? Rearrange it? You take the square root of it?
Oh yeah, that's wrong. Yeah, you square it.
Yeah.
So. Better?